Hello everyone. Welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. Well, my name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to ESO Paranal Observatory. So just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the Paranal Observatory since 2010, and I have also worked for an astronomy center in the University of Antofagasta. So I am well. I have been working with this subject for a long time, and but as I told you already, I am not alone. I am with the producer Hector Salas. How are you, Hector?
Hi, Farid. Happy to be here once again. So, I'll introduce myself. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related to the circumgalactic medium, that is the environment that immediately surrounds galaxies, and I have been a member of the team of guys for Paranal Observatory since 2019. I started while I was doing my master's in the University of Antofagasta. And today I'm the producer, so I'll be changing the pictures, the videos, but also I'll be reading all your comments. So please, if you have any questions, any doubts, just send them, and during the tour, we'll have a couple of times to answer any questions you might have. Um, yeah.
Okay, thank you very much, Hector. So yeah, ISO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember to send your questions or comments. Hector will collect all your questions, and we will have some time later to answer them. Yeah. And of course, you can share this experience with your friends if you want, with the share buttons on Facebook or YouTube. Okay, so we are going to start immediately, and we are going to talk a little bit about the organization, ESO. Okay, so this is in order to understand the place of our visit. So we are going to start with some information about the European Southern Observatory. ESO is composed of 16 member states. So we can see in this picture the countries, the ESO member states. So the headquarters of ESO are located in Germany, and also Australia has joined ESO in this case as a strategic partner. And Chile is the host state and home of all ESO observatories. Now, from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories such as ESO to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is basically to design, build, and operate astronomical observatories. And why? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now you will see a picture with the three observing sites of ESO in Chile. So first we have the Shahnator Plateau. This is the site of the ALMA radio telescope. ESO is part of this radio astronomy observatory alongside other international partners. In addition, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6-meter ESO telescope. And this one is using the HARPS instrument, and this is an exoplanet hunter. And finally, we have the place of our visit, Paranal Observatory. So this ESO observatory is the home of the Very Large Telescope, or VLT. This is the most advanced visible light telescope on Earth. And in the next few years, we will also have the Extremely Large Telescope, or ELT. And this will be the biggest visible light telescope on the planet. Also near there, the CTA will be an array of telescopes focused on capturing gamma rays. So now we have a better picture, and now we are going to travel to the Paranal Observatory. So now we have um, we are virtually flying over the desert and in the north of Chile, about 1,600 kilometers north of the capital Santiago, specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Tal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. So this mountain belongs to the coastal range, and despite its altitude, it's located at just 12 kilometers from the coast. And where's the ocean? Well, the Pacific Ocean is located below of the cloud cover that you see in the horizon. And why those clouds? If right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt stream. So this is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. Above the layer, instead, we have the hot, dry, and less dense air. So this is basically the good air for astronomy. The clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, what other natural barriers we have around this area? Well, about 200 kilometers to the east, we have the Andes Mountains, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. The main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity, I mean the light pollution. So overall, this is one of the best places on Earth for astronomical observations. Right now, we will change the view to have an even closer look to Paranal. So as you will see in a few moments, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are in the summit of Cerro Paranal. So do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. This observatory is a true oasis. So you will see how in one of the driest deserts we have a lot of life, but of course we have also a lot of science. Okay, so right now we will visit the summit of Paranal. And here we are. So in front of us we have the Very Large Telescope, or VLT by its acronym. If you see the amount of buildings here, I mean four giant domes, okay, and other four small and rounded ones, you can see here. Well, it is clear that the Very Large Telescope, in fact, is not only one, okay, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you can find in the front view the four unit telescopes, or UTs, each one with a primary mirror of 8.2 meters in diameter. Okay, so it's basically the giant ones in your screens. And the other small telescopes, I mean those ones, are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. So each UT, I mean the big ones, they have a name in Maputungun. This is the language of the Mapuche people from the south of Chile. So in first place we have Antu, and Antu means sun in Mapudungun. This one is Cuyen. Cuyen means moon. This one is Melipal, and Melipal means 4 stars, but this is a reference to the Southern Cross constellation. And the last one is Jepun, and Jepun is a reference to the planet Venus. Okay, so essentially all of them have astronomical names. And coming back to the small ones here, I told you already these are the auxiliary telescopes. The auxiliary telescopes are very special because they are mobile. Okay, so we can move the auxiliary telescopes using this kind of rail here. Can you see? So we have something like a rail system, and we have this kind of stations here, the ground. We have 30 different positions. So basically we can move the small ones and we can change the position to any station we want. So basically we can change the distribution of the small telescopes, so the small ones can be in a more compact or more extended configuration. Okay, so we can basically change the distance between them, and they were specifically designed to work all together as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a short video. So this technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. So in this animation, you can see that essentially we need to um, send the physical light received by each telescope to underground tunnels. So in the underground, this physical light will will reach at the same time a single point of combination. This is the interferometry building. I mean this building in the center of this platform. So this is what happens when you are working with interferometry with the small ones or the big ones. Yeah. Okay, so right now we are going to change the view and let's come back to the tour screen, because now you will have the opportunity to visit a telescope. I mean, one of the big ones. We are going to access this telescope. We are going to access to the UT3 or Melipal. We can't enter all the telescopes, but don't worry about that because the 4 ones are identical in size and shape. So the only difference are the instruments inside. So you can know more about the instruments if you visit, of course, the ESO website. Okay, so now we are going to enter the UT3. And here we are. So what can you see? Well, this is a giant telescope, right? We are at the last floor of this telescope, at the same height of the main mirror in front of us. So the mirror, I am going to do a close-up so you can have a better look. This mirror, well, it's heavy. It's 22 tons with 8.2 meters of diameter and only 17 centimeters thickness. This mirror was created from a ceramic and flexible material. The name of this material is Cerodur. And the surface, the material in the surface is a very thin layer of aluminum. Okay, so basically this is the material, the reflective material, okay, to reflect the light from the stars. So this this mirror, you need to understand that during the night, when we need to observe different astronomical objects, this telescope needs to point to different locations in the sky. So we need to tilt the telescope, and the mirror, of course, will be tilted, will have an inclination. And because the mirror is so heavy, 22 tons, and because this mirror is concave, okay, so it's like a spoon, you can expect that the mirror can suffer some deformations, some distortions, just because of gravity, physics, because the mirror is heavy, the mirror is tilted, so we can expect some deformations. And the problem is that those deformations can affect the quality of our pictures. Okay, so we need to do something about that. And of course, we need to also do something to avoid that the mirror could break, right? For example. So essentially, in order to understand how we can point this telescope to the sky and without breaking the mirror, and how we can keep under control this kind of deformation I was explaining before, I will show you the telescope from another perspective. I will go down because I want to show you something from this location. As you can see, we are in a different level. You see, we are basically underneath, and I can show you the telescope from this position, and you can see from here that the mirror is mounted over this white structure. Okay, so this is a cell supporting all systems assisting the mirror, including something called active optics. Okay, so I am going to do zoom in to show you something here, uh, because here you can see some little gray boxes. Do you see? They are called actuators. They are a kind of piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror. Otherwise, it could suffer deformations just because of gravity. Okay, so those deformations, imperceptible in a first view, could be critical in the result of the observations. So essentially, with these actuators, we can preserve the concave shape of the mirror because the actuators will do a small pressure. Okay, so we are going to compensate any distortion. That's why we call this technology active optics, because we are doing some kind of active action on the mirror in order to keep the same concave shape and to preserve the quality of the final picture. Okay. Okay. So this is what happens here. This is what happens regarding the active optics system. But now I want to explain a little bit about how the telescope is catching light at night. So in order to explain that, we are going to watch a quick short video, an animation, in order to understand this. So as you can see here, the first step is to open the dome. Okay, of course, this is exaggerated in this animation. So we need to open the dome. The light will reach in first place the primary mirror, and because the primary mirror is concave, the light will be concentrated and will be reflected to a secondary mirror in the top, and the light will be reflected again down, and down we have a tertiary mirror, a flat mirror. So we are going to reflect the light to one of the possible instruments. In this animation, we have this red, blue, and green, well, let's say boxes representing the instruments. Okay, so we have three different instruments per telescope, and we can use one instrument for a single observation. We cannot use the three instruments at the same time, but we can use a different instrument per observation because the instruments are different. So in this picture, for example, you can see here one of the instruments, and of course it's very, very big. is it's a very complex camera, of course. And in the other side, well, it's not visible from here, but we have another instrument here, and we have another instrument interface. So from this picture here, you can see this is the primary mirror, this is the secondary mirror. This mirror is convex, and the tertiary mirror is not visible here because it's blocked by this structure, but it's in the middle. Okay, so in the middle we have a tertiary mirror, and this tertiary mirror is flat. So and the tertiary mirror can be lifted when we need to use the instrument interface. So essentially, we can reflect the light with the tertiary mirror to go there, to go to the other side, or we can lift the mirror so the light can go down to be received by the instrument here. So essentially, we can choose the instrument per observation. And something very important regarding the instruments and the telescope and the machines in general is that during the day we have a team of very qualified engineers to do some maintenance, to fix some problems. So that's why in this picture, for example, you can see some of them. We have some engineers working in this picture. So basically, they are preparing the telescope for the next observation night. Okay, so essentially, the work during the day is for engineers, and the work during the night is for astronomers. Okay, so that's it. This is the explanation about the telescope, one of the big telescopes. So now I am going to go outside because the next stop will be the workplace for astronomers. I mean, the control room. So in order to visit this place, well, we need to go to this location, this different facility. This is the control building. As you can see, this place is in the same mountaintop, but it's in a different, let's say, level. It's not. It's in the same telescope platform. So the control building, I will show you this building from another perspective. Is this place, and this is basically the workplace for astronomers at night. But before going there, this is a good time to check if we have any question from our virtual visitors. Okay?
Yeah, we don't have any questions so far, so let me ask you one of the usual questions we receive. What kind of maintenance is necessary for the telescopes?
Yeah, sure. This is very, very important. In order to keep the telescopes and the mirrors specifically in the best shape, we need to do some maintenance, and I will access again many parts to explain this. So the mirror is the most delicate part of each telescope. So as you can see, the mirror looks like new, looks very nice, looks very clean. You need to understand that Paranal was inaugurated in the uh, what, more than 20 years ago, in the 1998. So in order to keep the mirrors clean, we need to do two different maintenance systems. One of them is necessary once a month, and in order to do this, we need to tilt the mirror a little bit, and a couple of engineers they will spread a carbon dioxide snow on the mirror. This is something like a foam to remove dust, because while we are in the desert, we have dust in the environment. So it's necessary to remove dust, and we need to use this carbon dioxide snow. So this is a non-invasive procedure, and we need to do that only once a month. And we can keep the mirror clean in general terms. But we need to do another maintenance, and this is more complex. This is necessary every 2 years. And in order to do this, we need to extract all the mirror from this facility. So we need to use a special crane to extract the mirror and the white base, the white cell. So I will go outside because I want to show you that in this picture, you can see a yellow structure here, right? So when we need to remove the mirror from the telescope, we need to place the mirror here in this structure. So at the ground level, we will have a special vehicle. So we are going to drop the mirror very gently, of course. So we are going to place the mirror in this vehicle, and the vehicle will transfer the mirror down to the base camp, and we need to essentially transfer the mirror to another facility, a mirror maintenance building, and in this place we can do a recoating. So the recoating is essentially to remove the aluminum layer and to put a new one. So at the end of this process, after 3 or 4 days, we will have the same original cell, the same original structure of the mirror, but we are going to change the aluminum layer, the surface. So the mirror will look like a new mirror in the end. So we need to return the mirror to the telescope. We are going to use the same structure to lift the mirror, and we need to reinstall the mirror in the telescope, and the mirror will be ready again for observations. So that's the main maintenance process for the mirrors, and that's why in Paranal we are using the same original mirrors for more than 20 years.
Okay, thank you for it. And maybe before we continue, you can tell us about how to visit the observatory in person for those who has the chance to do it.
Yeah, sure. In Paranal, we have a public visits program every Saturday. We have two different times for a virtual tour. I mean, for a tour in person at 10 a.m. and 2 p.m. So, in order to visit Paranal, you need to visit the ESO website, and you will find a section about the public visits program. You need to do an online booking in advance, maybe 2 weeks in advance, and you can select your, I don't know, if you want to go on the morning tour or the afternoon tour. The visit is completely free, but you need to use your own transportation from the closest city. Antofagasta is about 1 hour and a half of time travel. Maybe you need to plan to, I don't know, 2 hours for safety. And when you arrive to the observatory, the tour takes about 2 hours and a half. So basically, you will visit all this facility during the day, and of course you have tours in Spanish or English, and yeah, essentially this is all you need to know. So I recommend, if you want to visit Paranal in person, please try to do an online booking in advance, maybe 2 weeks in advance, because we have limited spots to visit the observatory.
Okay, thank you. I think we can continue, and I would like to invite our viewers to send any comments or questions they may have, and we have a second round to answer them later.
Okay, thank you so much, Hector. So we are going to continue now. And as I was explaining, the next stop will be the control building. So we are going to move to this location. Um, the control room is the workplace for astronomers, you remember? So we are going to visit this place in order to understand what happens inside at night. Okay, so as you can see, the control room is like an office space. It's not a futuristic location. It's just well, you have of course different workstations and a lot of computers, because you need to do all the remote operations from here. So essentially, you have different workstation per telescope. Okay, so in this workstation, for example, you have some people working. And the computers here are to do all remote operations for only one specific telescope. In this case, Melipal. So only operations with Melipal are from here. Okay, so if you move to the other workstation in the front, this workstation belongs to another telescope. This one belongs to the UT4 Jepun. Okay, so only operations with Jepun are from here. Okay, and it's the same thing. We have different different computers for different purposes, and we have some people working there. So essentially, uh, all the telescopes, instruments, and systems explained before are controlled from here. Okay, this is what happens here. And you don't need a lot of people at night, maybe 10 or 15 people, usually one telescope operator and an astronomer per workstation. Okay, here I am in another location of this control room, because I can show you here the workstation for AN2 UT1, and you can see it's the same thing, different computers for different purposes. And in the opposite workstation, we have Kuyen. So this is the workstation to do the remote control of the Kuyen telescope. So I am going to access this one to show you a closer look. So as I told you already, for each workstation, we need a telescope operator and an astronomer, usually. Okay. So for example, in this picture, we have the computers, and this person is a telescope operator. Okay. So the telescope operator is basically the person in charge of the technical details and the movement of the telescope. So he's essentially like the pilot of the machine. Okay. But the ESO astronomer is in charge to direct the scientific observations, and this person will decide the next steps. So it's like the co-pilot. So let's suppose that this person is the astronomer. Okay, so this is what happens here. Essentially, you have people working per telescope. They are working all night. They are doing everything remotely, so you don't need to be in the telescopes at night at all. You can do everything from this specific location, the control room. Okay, so the observations, of course, are performed by experts from ESO for scientists from any country. In case you have the possibility to get telescope time. Okay, so this is essentially what happens here. This is not a super big place, so I am going to go outside now, because now we have time to explain something else. Because right now you have a lot more information about this observatory and the people working here. But now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor, because scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, but also others located in the more distant places in our universe. So now we are going to explore a list of the top 10 discoveries from the ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today. the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. I hope you like it. We have just one more thing. We have something like a bonus track. Let's take a look at this now. This is not so recent news. It's something from some years ago, but it's very, very important. A team of astronomers was able to capture the first picture of a black hole. The Event Horizon Telescope, or EHT, its acronym, an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, was able to achieve the first direct evidence of a supermassive black hole, as you will see in a few moments. The picture will reveal the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. This object is located 55 million light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so this is the picture, and we hope you liked the top 10. This was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific staff behind them. So now we can continue, and from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. The moon is below the horizon, and the sky is full of stars. So I am going to show you some interesting regions and objects. So first, we can see a very popular constellation just above of the N2 telescope. Okay, so I am going to do a close-up here. I will show you this better. And we can see here that this is the very popular Orion constellation. Okay, in the mythology, Orion represents a hunter, and you can recognize Orion with those three stars, right? Somewhat aligned, representing Orion's belt. And inside of Orion, and very well, next to the three stars here, we can see something, right? We can see another interesting object, and this object is the Great Orion's Nebula. This is a star-forming region. It's very bright, it's very big, so you can see the Orion's Nebula even with your naked eye in a dark and clear night like this one. Of course, it's only like uh, also it's like a spot in the sky. But of course, in order to see more details, you need at least some kind of binoculars or even a small telescope. But it's a beautiful object, and it's visible from the southern hemisphere and the northern hemisphere. Okay, so now we are going to change the position and move to the brightest star of the night sky. And the brightest star is called Sirius. So Sirius is this star. This one here is the brightest star in the sky. And this star belongs to another constellation. It belongs to the Canis Major constellation. So Canis Major is essentially in the mythology one of the hunting dogs of Orion. So essentially the constellation of this star, the brightest star in the sky, is connected in the mythology to Orion. Okay, and again is visible from both hemispheres. Okay, so if we go down, little bit down, and next to N2, next to the telescope here, we can see another interesting object. This object is right here. So what is this? This is the Pleiades. This is an open star cluster located in the Taurus constellation. And usually in a dark and clear night like this one, you should be able to observe at least 7 stars. That's why in the mythology they are also called the Seven Sisters. But this is an open cluster composed of millions of them. Okay, so now if we pay attention to this area in the sky, the majority of those objects are visually close to a very specific area, very populated with stars. So if you look carefully, you can see that this area have a more concentration of stars if you compare with this area or this area. So this is essentially because we are looking at one of the Milky Way arms. This is our galaxy, and our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between the Scorpius and Sagittarius constellations. Okay, and you can see all this area from this hemisphere. So essentially, during the winter in the southern hemisphere, I mean, end of May, June, July, you can see the center of the Milky Way, and this is of course beautiful. Okay, we are going to change the position of this uh, virtual tour because I want to show you something um, to this direction, to the south. We are going to focus our view on those spots. Okay, those spots here, right here, are the Magellanic Clouds. Up there is the large Magellanic Cloud, and down there we have the small Magellanic Cloud. They are not actually clouds, of course. They are galaxies with an irregular shape, both visible to the naked eye in a clear night like this one. Um, this name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, of course, the people have no idea about what a galaxy is. And the Magellanic Clouds are only visible from the southern hemisphere. So you cannot see them from Europe or North America, for example. Now, another important area right here, if we continue looking at the south, is the smallest constellation in the sky. I mean, the Southern Cross. The Southern Cross is located there. Okay, so I will do a close up, and you can see here we have the Southern Cross. In this picture is tilted, right? This is an easy constellation to find in the sky. This one is also only visible in this southern hemisphere, and this is a good guide to find the south celestial pole. This is a projection of the Earth's south pole. So during the night, the stars appear to revolve around this point. I mean, the south celestial pole. So in order to find this point, we have to do something. We have to use the Southern Cross, and we need to do something like extension, of course, in our imagination, extension of the longer stick of the Southern Cross. So we need to do this like about 4 times and a half. So it's something like 1, 2, 3, 4.5. And more or less like here, we have the south celestial pole. So during the night, if you try to take a long exposure astrophotography, the stars will appear to revolve around this point. Okay, and if you consider this point and you look exactly to the ground, I mean to the horizon, you are actually looking at the south cardinal point. Okay, so this is a good way to find the cardinal points if you want to only use the stars. Okay, so this is the conclusion of our visit to Cerro Paranal. So we are going to come back to the platform like before, I mean daytime, because we have one last stop before finishing this virtual experience. We have to visit the residence. So in order to visit the residence, we have to change the view, and we have to focus our view to visit the base camp. The base camp is located there. Okay, this is another important place in this observatory because we have, for example, rooms for contractors. We have some offices for the informatics. We have the mirror maintenance building. We have a gym. We have a lot of different facilities for the people working here because we have something like 130 people in the observatory. And there we have this place I want to show you now because we have the residence here, and the residence is a very special place because this is the place where the ESO staff can stay and rest. So the residence is essentially the home of the ESO staff when they are working in the desert. you need to use this ramp to access this place. This place is not exactly underground. This is just taking advantage of the shape of the land. Okay, so you are accessing using this ramp. This is the roof, but in the other side, in the opposite side of this residence, you have basically a lot of windows, like any normal building. So this is not exactly underground. Okay, I am going to access now, and you can see the inside here. So essentially, here the workers can enjoy a more humid air. They have, as you can see, a swimming pool. They have green areas, and of course, other important facilities. Well, you can see the restaurant over there. We have a lobby. We have a reception. So essentially, it's like a hotel, but it's only for the staff. This is the only difference. We have 108 rooms. You can access the rooms using this corridor, and essentially, it's, well, as I told you already, it's only for the staff, so it's not for tourists. Okay, so we are going to finish here the explanation, and before finishing this virtual experience, I don't know, Hector, if we have some questions from our visit.
We don't have any more questions from our viewers. Um, so I think we can just start wrapping things up. So we're almost 55 minutes into the transmission. So for my part, I want to remind everybody that we're doing these virtual tours every Saturday. We are alternating between Paranal Observatory and La Silla Observatory, also between Spanish and English. So please keep an eye out in our social networks to see when the next tour is going to be, in which language, and please share it with everybody you know that might be interested in this type of content.
Yes, of course. So thank you very much to our virtual visitors, and we remind you that all those visits, information, and pictures are available on the ESO website. So you can know more if you visit the ESO site. And yeah, we have some tours every week in Spanish or English, Paranal or La Silla. Okay, so well, I hope you like this virtual experience, and on behalf of ESO, I want to say thank you very much for your presence and